guys. All right, on this video, I'm going to do an introduction to probability. All right, so that's going to be kind of where test 2 begins, but we need to kind of go ahead and get started on it. All right, so let me pull up my PowerPoint, I hope, and kind of talk you through it. All right, so they're going to be two kinds of probability. All right, and you're going to have to be able to do both of them. All right, so one kind is called empirical probability, and the other is going to be called theoretical probability. Now, that's not what the book calls them, but this is what mathematicians call them, and it's easier than what your book calls them. Okay, so I need you to remember that empirical probability is based on experiments. All right, so if I ask you what's the empirical probability of doing something, you've got to go actually do the experiment. Okay, and what you do is you end up with a fraction. All right, so look how you get the fraction. The numerator, the top number, is the number of times the event occurred, past tense, you have to have already done it. And the denominator, the bottom number, is the number of times the experiment was performed. All right, so what do I mean by that? Okay, now let me get a piece of paper so I can kind of do this as we go. All right, so what if I told you this? What if the problem said, what's the empirical probability of getting heads when flipping a coin? Then I've got to go get a coin. So I went and got a penny. All right. So one of the things I need you to start doing now that's going to seem a little silly, but it's going to save your life later. When you're doing probability, you put down a P, and in parentheses, I need you to write what you're trying to find the probability of. So this is your event. Okay. So it said, what's the empirical probability of getting heads when flipping a coin? So I need you to put the probability of heads. You might put getting heads. So the exact wording might be different, but the event you're looking for better be in this parenthesis, or you're not going to give you any partial credit. All right. So what I'm going to have to do now is I've got to start flipping a coin. Now, so you kind of write down on your paper an H and a T, and you help me keep track of what we're getting. All right. So I'm going to flip this coin. Whoops. All right. I got heads. All right. So mark down that you got a heads. All right. This time I got tails. Let's do it again. All right, I got heads again. All right, here we go. Whoops, I got heads again. All right, let's do it again. Flip. All right, I got heads. I'm getting tired. Let's do one more. Surely, tails. Thank goodness. Okay. All right, so if I wanted to, on the top, I've got to put how many times I got heads. Okay, so this top number is how many times you got heads. And it looks like I got 4. Hopefully that's what you got. All right, so I got heads 4 times. The bottom's the number of times the experiment was performed. So my experiment was flipping a coin. So how many times did I flip? Didn't I flip a total of 6 times? Now, the reason I won't take this as an answer on a test is it's not reduced. So you've got 2 choices on a test. You can give me a fraction reduced to simplest form. So I would take 2/3. Or you could give me an approximate decimal. All right, to about 3 or 4 decimal places. So if you take 4 and divide by 6, you take 2 and divide by 3. All right, you're going to get, it's a bunch of repeating 6s. Okay, so I'm going to stop and round. So 0.667, that's a decimal. It didn't look much like a decimal, does it? Okay, so I would take either one of these, an answer in a fraction in simplest form or a rounded off decimal. And make sure you're not rounding up or chopping off. You're correctly mathematically rounding off. Now, do you see that if I flip the coin 6 times again, I might not get the same answer? If you flipped it 10 times, you don't get the same answer. Okay, so one of the problems with empirical probability, it moves around on you. Okay, because it's based on experiments. Okay, now the other way to get probability is theoretical, and it's based on theory. So look at the difference in kind of this formula and this one. The top number here is the number of ways the event can occur. So possibility. And the denominator is the total number of possible outcomes. Okay, so think about it. When you're flipping a coin, what are all the things you could get? I'm going to put H for heads. You'd get heads, or you could get tails. So what's the theoretical probability of getting heads when flipping a coin? Well, on the bottom, look what it says, total number of possible outcomes. So when you're flipping a coin, do you see you can only get 2 possible outcomes, either heads or tails? All right, of those 2 outcomes, how many are heads? Only 1. So you could give me 1/2, or you could give me 5/10. Now, do you understand that everybody would have to get these answers on theoretical? So everybody gets the same theoretical probability. Everybody doesn't get the same empirical probability. So why don't we just do theoretical and be finished? Well, here's why we don't do theoretical and be finished. Sometimes you can't do theoretical. Look at why. That denominator says total number of possible outcomes. Well, if you can't list the possible outcomes, you can't count them. So when you're doing things like picking a prescription up and you read on the back, there's a 1 out of 1,000 chance you're going to get a headache. Where did they get that probability? Well, it was empirical. They did experiments using the drugs. And that's how many people had headaches. I don't know how many times they gave the drug. So it's an empirical probability. You cannot do theoretical probability with drug testing. I mean, who knew that you were going to turn purple and break out in lime green spots? Who knew that? Couldn't predict that. So you can't actually know every possible reaction a person might have to a drug. So if you don't know every possible reaction, you can't count them. So sometimes in the real world, you can't do theoretical probability. And so you have to do empirical. If you have a choice, you're going to do theoretical. It's just not always possible. So that's why there's 2 kinds. Empirical is based on experiments. You have to actually go do the experiment. Theoretical is based on theory. Now, let's look at this next thing. There's some facts on the next slide we need to talk about for a minute. Sample space. A sample space is an actual list of all the possible outcomes. So if I tell you to write me the sample space of something, you've got to individually list every possible thing that you could have. So if I said, what's the sample space of rolling a die? Now, you know what dice are. Little cubes with dots on them, like when you're playing Monopoly. Well, dice is plural, die is singular. So that means I've got 1 little cube. So think about when you roll 1 of those little cubes. All right. Everything that's on them, there's a 1, a 2, a 3, a 4, a 5, and a 6 on a regular die. So this is the sample space of rolling a die. What's the sample space of flipping that coin I had a minute ago? Well, there are only 2 things on that coin, heads and tails. So a sample space is an actual individual list of all the outcomes. Okay, so if you can't write down the sample space, you're not going to be able to do theoretical. That forces you back to doing empirical. Okay, now look what the law of large numbers says. Now remember, which probability jumps around on you? You remember that empirical jumps around? So look what it says. It says the more times an experiment is performed, the closer the empirical probability tends to get to the theoretical probability. Now, what does that mean? All right, well, let's go back to this slide we had a second ago. Now, remember what we had. Let me back up here and get my little pencil. When we did empirical probability, if I remember right, we got about 0.667 for our empirical probability of flipping a coin and getting heads. And then we got 5/10 for our theoretical probability. Now, they're not the same number, but we only flipped the coin 6 times. I bet if we had flipped the coin 60 times, this number right here would be closer to 5/10 than it is. If we flipped it 600 times, I bet it'd get even closer. 6 million times, I bet it'd be really close. So do you understand? It says the more times you do the experiment, the closer that empirical probability gets to that fixed theoretical probability. Okay, so that's the important of that law of large numbers. That's why you have studies repeated. That's why you want more than just a few things in your sample. So that's what that law of large numbers says. Now, you're going to hear me say this thing in the box in your sleep by the end of the time we finish with probability. Probability is always. Now, we don't say always very much in math, so you need to pay attention. Probability is always a number between 0 and 1 inclusive. So it can be exactly 0, it can be exactly 1, or any number in between the two. But you cannot get a correct answer that's bigger than 1, and you cannot get a negative answer and be right. So look what this says. When an event is impossible, it cannot happen. The probability is 0. When an event always happens, it is certain to happen. The probability is 1. So never and always. And everything in life is somewhere between never and always. So here's an example to kind of illustrate that. Like a regular die, remember? Here's what's on a regular die, 1, 2, 3, 4, 5, 6. So I say, what's the probability of rolling a regular die and getting an 8? So I have a P, I'm looking for an 8. On the bottom, remember, is the total number of possible outcomes. So there are 1, 2, 3, 4, 5, 6. That's why there's a 6 on the bottom. Of those possible outcomes, how many are 8s? None of them. So there is a 0 probability of getting an 8 when you roll a die. It is impossible, not going to happen. Well, what's the chance that when you roll a die, you get a number less than 8? Well, again, on the denominator, all the number of possible outcomes, there are 6 possible outcomes. Of these 6, how many of these numbers are smaller than 8? All 6. And 6 divided by 6 is 1. You are certain to get a number smaller than 8. So never, 0, always 1. So don't write an answer bigger than 1 on the test. If you know it's not right, at least write me a note and go, I know this isn't right. Okay, so I don't laugh at you. Okay. All right, now let's go look at this next slide maybe. All right, so probability is always a number between 0 and 1. Those are your extremes. 0, never going to happen. 1, always going to happen. Now, I do want to make sure we're clear about this. There's a difference between saying an empirical probability is 0 and saying a theoretical probability is 0. An empirical probability of 0 just means so far this has not happened. But it doesn't mean it won't. So a theoretical probability of 0 is much more powerful. It means not only has it never happened, it means it never will. I mean, I could have flipped that coin 6 times and gotten heads all 6 times. Or I could have flipped that coin 6 times and not gotten heads at all. But that wouldn't guarantee what I was going to get. So an empirical probability of 1 means it's always happened and it always will. That's a theoretical probability of getting 1. It means it's always happened and it always will. An empirical probability of getting 1 means so far it's always happened. But you can't guarantee what's going to happen the next time. Okay? So theoretical probability is more powerful than empirical probability. Okay? Now look at this idea of a complement. If I tell you that my personality and my husband's personality complement each other, does that mean that we're exactly alike? No. It means what I don't have, he does. What he doesn't have, I do. So we kind of make up for each other's deficits. Okay, so we go together to be a complete thing. Well, that's what complements mean in math. Either you roll a 2 or you don't roll a 2. Now, I know that you could roll a 1, a 3, a 4, a 5, or a 6, but I could lump all those together and just call them not a 2. What's the complement of living? Well, either you live or you don't live. Normally we don't say don't live, we say die. So live or die. You pass or you fail. Okay, you're married or you're not married. Okay, so complements, when you know one, you automatically know the other one. And so you know the probability. So think about it. If they told you that Wednesday the chance of rain is about a 2 out of a 5 chance, well, either it rains or it doesn't, then what's the chance it's not going to rain? See, that's right. You said that without me even telling you how to do it. You said, well, if there's a 2 out of 5 chance it will rain, there's a 3 out of 5 chance it won't rain, the rest of it. So do you understand that when you know the chance something will happen, if you subtract from 1, you get the chance it will not happen. So the chance that it's not going to rain is 1 minus the probability that it will rain. Now, when you're subtracting and adding fractions, you have to have a common denominator. So what's the smartest way to write this 1? Yeah, I'd write it as 5 over 5, so I'd already have a common denominator. I mean, you could write it as 3 over 3, but that's going to make more work. And so 5 out of 5 minus 2 over 5 is where we got 3 over 5. So if you know the probability something will happen, subtract from 1 and get the probability that it won't happen. Now, if they gave you percents, what's all of something in percents? Wouldn't that be 100%? So if there was like a 10% chance of rain, there'd be a 90% chance it's not going to rain. Okay, so when you know the chance something will happen, you subtract from the whole to get the chance it will not happen. Okay, so it says, what's the probability that you do not pick a king if you pick one card from a deck? So what's the probability that I'm not going to get a king? Well, it's going to be 1 minus the probability that I do get a king. So I've got to go do this probability. Remember, what goes on the bottom is the total. Now, if you don't know something about cards, you need to learn them. There are 52 cards in a deck, and there are 4 suits. I'm not trying to get you to play poker. All right, maybe surely you played like Go Fish as a child. But if you didn't, you need to memorize. So 52 cards in a deck, 4 suits. You can have hearts, diamonds, spades, or clubs. So if you take your calculator and divide 52 by 4 suits, that means there must be 13 of each one. So there are 13 hearts, 13 diamonds, 13 spades, and 13 clubs. So the hearts and diamonds are red cards, and the spades and clubs are black cards. So half, 26, are red, and the other half, these 26, are black. There's an ace of every one of those, and there's the numbers 2 all the way to 10 on the cards. And then you've got some cards they call face cards. You can have jacks, queens, and kings. So you'd have like a jack, queen, and king of hearts, and a jack, queen, and king of diamonds, and so forth. So you'd have 12 face cards. So that's why there's a 52 on the bottom. There are 52 total cards. Well, how many are kings? Well, again, there's a king of hearts, a king of diamonds, a king of spades, and a king of clubs. So there'd be 4 kings. Well, I need a common denominator, so 52 over 52. So I get 48 over 52. Those will both divide by 4. So I could reduce and get 12/13. That'd be a great answer. Or you could take 48 and divide by 52, and again, round to 3 or 4 decimal places, 0.923. Now, the only time you've got to go more than 3 or 4 decimal places, I do not want you rounding to 0, and I do not want you rounding to 1. So if you've got to go 12 decimal places, 0.000000000002, then you do that. Okay, so don't round to 0 or 1. As long as you don't have to round to that, you can go 3 or 4 decimal places. Okay, so complements, when you know the chance something will happen, then you can subtract from 1 or the whole to get the chance it will not happen. Okay, so let's go talk about the difference in odds and probability, because most people in the real world think they're the same thing, and they are not the same thing. All right, you use probabilities to make odds. Kind of like you use bricks to make a house, but the bricks on the house are not synonymous. So we're going to use probability to build something called odds. So odds are a comparison of 2 probabilities. So you're going to have a fraction over another fraction. So anytime it says odds, you're going to have the probability that something will happen and the probability that something will not happen. All right, so there's 2 types of probability. All right, and there's 2 types of odds. You can have odds against, or you can have odds in favor. Now, both times, you know the probability that something will happen, the probability it will not happen. The difference is which one goes on top. So when it's odds against, the probability that an event does not happen goes on the top of the probability that it will happen. So not goes on the top. Odds in favor is the flip or the reciprocal of that. On odds in favor, the probability that the event does occur goes on top of the probability that the event does not occur. So look at this. What are the odds? Now, as soon as it says odds, I go find the chance something will happen and the chance it will not happen. So what are the odds against picking a heart? So I find the probability that I will get a heart and the probability that I will not get a heart. Now remember, there are 52 things in a deck. How many are hearts? Remember, there are 4 suits, so there are 13 hearts. So I reduced that and got my chance of getting a heart is 1 out of 4. So what's the probability that I'm not going to get a heart? Well, it's 1 minus the probability that I do get a heart. Okay. And again, I need a common denominator, so I changed that to 4/4 and got 3/4. So there's a 1 out of 4 chance that I will get a heart and a 3 out of 4 chance I will not get a heart. So these are complementary probabilities. Okay, they're not odds, they're probabilities. Now, how do I get odds? I put one of these fractions on top of the other fraction. Well, how do I know which one to put on top? I look at what kind of odds. All right, this says odds against. So with odds against, the probability that the event does not happen goes on the top. So the not, the 3/4, went on top of the 1/4. So there's the probability that it will not get a heart over the probability that I will get a heart. Now, you've worked problems like that since 4th grade. They just didn't look like that. They looked like this. This is 3/4 divided by 1/4. And most of you multiplied by the reciprocal. So remember, the first fraction stays the same. Division turns into multiplication. You flip this last one. And remember, look at those 4s are going to go out, and it's going to leave you 3/1. Now, with odds, you have to have 2 numbers. You can't just put 3. That's red, 3/1. A lot of times you'll see it written as a colon, so you don't think it's a fraction. That's what's called a ratio, 3/1. So that means for every 3 times that you don't get a heart, 1 time you would get a heart. That'd be the average. Well, what if instead it said, what are the odds in favor of picking a heart? I would have done this exactly the same way. It's just when it says in favor, the probability that the event does occur would go on the top. So my 1/4 would have gone over my 3/4. So notice, when this bottom number matches this bottom number, they're going to go out and just leave you this top number 1 over this number 3. And that's read 1 to 3, not 1/3. All right. So that means for every 1 time you get a heart, 3 times you would not get a heart. So when you know one of the odds, you just flip it to get the other one. You don't have to work the whole problem over. Okay. Now, the reason that's such a big deal is in the gambling world, that's the way the bets are paid. All right, let me kind of show you what I'm talking about. Let me teach you to gamble. All right, suppose you go to the Kentucky Derby and you bet on a horse. All right, thrilling 3.5 minutes. Okay, so look at what I say. All right, you found this horse you want to bet on, and it says the odds are 5-2. Now, first of all, that means the 5 is on the top and the 2 is on the bottom. All right, so you can write odds like this. A lot of times in betting, they write them like that. Now, first of all, to make sure we understand, if it just says odds, it's always odds against. It's the most common. So I know that it's odds against. All right. So the top number and the bottom number, or the number in front of the colon or behind the colon, are very specific. The number to the right of the colon is your bet. The number in front of the colon is what you win. So that would say for every $2, you would possibly win $5. So this top number is what you win. This bottom number is what you bet. So I say this, if you bet $10 on the horse, what would you win if the horse finished first? So, you know, you're betting on Old Dominion. You got $10 on Old Dominion and he wins. How much money do you win? Well, do you understand for every $2 you bet, you'd win $5? So if you bet $10, you kind of bet 5 groups of 2. Each one of those $2 would win you $5. So you should win $25. Now, to me, an easier way of looking at it is to set up what's called a proportion. And notice, on the top is what you're winning, on the bottom is what you bet. So it's 5-2. So is this $10 up here what you bet or what you won? It's what you bet. So that's why it went on the bottom. And then you do what you think of as cross multiply. Product of the extremes. So 5 times 10 is 2 times x. So when you divide both sides by 2, you would win $25. Now, in case you actually go to the horse races, let me make sure you understand. When you go to the window, they're not just going to hand you $25. Or you're getting ripped off. You're supposed to win $25. So see, if they just handed you $25, didn't you pay $10 to play the game? then you really wouldn't be $25 richer. So they have to give you your winnings, your $25, plus they have to give your original bet back to you. So you would leave the window with $35. Your $25 that you won plus your original bet back. So think about it. All right, this is why people will bet on a horse that's 99 to 1. Now, think about what that means. Is this horse likely going to win? No, this horse ain't going to win. Because it's odds against. Remember what odds against means. So that means for every 99 times that this horse loses, one time this horse would win. So this is not a smart, so to speak, bet. So why do people bet on it? Because remember, that's also, if you bet $1, you'd win $99. So let's go back to this $10 bet. If it was 99 to 1 and you bet $10, remember $10 is your bet, so it goes on the bottom. All right, so do you understand that you do the cross multiply? So 99 times 10 is 990 equals 1 times x is x. So do you understand, if this horse just happened to freakishly win, you'd get $990 plus your $10 back. You'd leave the window with $1,000. Chances are you're going to lose either way. So it's going to be a thrilling 3.5 minutes. So that's why people bet on this. You never bet anything you can't live without. So you're paying for the experience, not really going to usually win. But that's why people bet on these horses. Just every once in a while, one happens to win and they win a whole bunch of money. Okay? So by the time we finish the probability, you're not going to be betting on anything, I'm pretty sure. Okay, then I know that I will have done my job. Okay, we'll talk about casinos later. Okay, smart people do not. Just know. Okay, now that's your introduction to probability. I'm going to put a homework assignment up that I would start working after my test. Okay, if you need some help, just let me know.